So in the previous couple of lectures, we took examples on distillations, right? So we had essentially two methods, McCabe-Thiele method and Ponchon-Savarit method. In today's lecture, we also take one more example on McCabe-Thiele method, however with slightly different objective. So you must have realized that most of the times we have made use of graphs. So it's essentially by graphical method we have addressed, like, how many number of trays are required, or what is the heat load in the reboiler of the condenser. In today's lecture, we take one more example. So this example will help you how we can solve analytically, writing those McCabe-Thiele operating lines, and see how we can substitute one variable from one equation to another equations. So this example is again on McCabe-Thiele method, but this will give you slightly different angle how we can write a programming code, or how we can solve algebraically by writing some equations here. So let's take this example on McCabe-Thiele method. So what we have here, for simplicity, let's say that we have only 3 plates. All right. So most of the times you had earlier when you were asked to find out the number of plates, but here we have been given that, let's say we have 3 ideal plates. So idea here is to solve non-graphically. Okay. So let's say the plate number 1, 2 and 3. Feed is sent between 2 and 3. So it's a general case, you can have more number of plates and the feed can be inserted anywhere. So let's say the flow rate is F and mole fraction is XF. Let's say we have ammonia plus water system. So it's aqueous solution of water. So this feed, let's say the composition, this feed is 0.005. Okay, and here we have, it's a saturated vapor. Okay, so if you recall immediately that when we say it's a saturated vapor, the feed is saturated here, we say that Q is 0. So that's your Q line. And let's say the thermodynamically we have these equations, y equal to 12.6x over the concentration range of our interest here. So we are trying to simplify here things here, that we have only 3 trays. We have this equilibrium line which can be written by these equations. Okay, that's one. Feed enters between second and third, and let's say the reflux is at bubble point. So it's also a such saturated liquid, and we have total condenser. All right. So essentially this vapor from the top plate comes to a total condenser. We have this top product, flow rate is D, composition XT, and we have this reflux with the composition X0, flow rate L0. This is Y1 here, this is vapor flow rate is G. Okay, so we have the same nomenclature. This is X0, we have L0 equal to L, vapor leaving from here, we have liquid dropping from here, so this composition would be X1, and this is top plate 1, so this is Y1, this would be Y2. All right, and the top we have, it says vaporizations. So in about this reboiler, the problem statement reads vaporization in the reboiler is 0.6 mole per feed. So we have this liquid which comes to the reboiler, we withdraw the product W, XW, and part of this vapor, or the vapor, is sent back to this reboiler as a reflux here. So that's given here in the reboiler. This flow rate of the vapor is adjusted so that we have this G bar. So this is your G bar, which is 0.6 times the feed flow rate, 0.6 into F here. Okay, so if this third plate here, you can say that this composition is Y4. Okay, this vapor flow rate is G bar, and what liquid trickles here is L bar. So we are following the same nomenclatures, L bar, G bar for this stripping column, and L and G for this rectifying sections. So the stream which is arriving at the plate third has the composition Y4, and this should be equal to X3. So this is again X2, and what here we have is this Y3. Alright, so with the same nomenclatures. Now this problem, other than this, we have been given this, of course, equilibrium data, and we have been asked to calculate the other quantities, remaining quantities, let's say all the mole fractions in the columns for the liquid phase and the gas phase, and the different flow rates, which is L, G, L bar and G bar. Okay, so how do we address this? Now if you notice that here we have given the number of plates, okay, and the feed flow rate is not given, but the other data are given, like what is the vaporization rate in the reboiler. Okay, so mole fraction is given XF. So first thing is that we will like to solve graphically. So we have this algebraic equation given for this equilibrium line. We are supposed to set up the operating line equations for both top column and the bottom column. So before we do that, let us see what are the other quantities which we can determine, okay, from the information of the data which is given to us. Now the feed flow rate is not given to us. That means we can choose a basis. So with the basis of F as 1 mole per second, the flow rate, let's see if we can compute some other quantities. Okay, so F we choose as a basis, 1 mole per second. Alright, now other quantities which should be interesting here is one more data is given here. The reflux is saturated liquid, total condenser. Okay, number 2, reflux is 1.3 moles per mole of feed. So when this is D here, your L0 which goes back at the reflux is R into D, if R is the external reflux ratios. Here reflux is 1.3 times per mole of feed. So when we choose F as 1 mole per second, L0 which is R into D, neither D is given nor R is given, equals 1.3, same units, moles per second. Now what is given here is G bar, reflux, vapor reflux, which is 0.6 times F. So we have this G bar as 0.6 moles per second. So F, L0, G is given to us. Now let's see if we can compute the other quantities. Now when we say saturated vapor, then we have Q equal to 0. That means at the feed plate, which is between 2 and 3, where the feed enters, saturated vapor, this goes with your vapor V or G, and this is your G bar. Liquid is L here, liquid flow rate, molar flow rate, and here we have L bar. So that means saturated vapor, whatever V, the top column we have, equal to whatever arrives V bar plus this F, or the following the same nomenclatures, we have G equal to G bar plus F. So G bar is reflux which is sent from the bottom column from the reboiler here, which is 0.6, and we have 1 feed we have chosen as a basis, we have 1.6 mole per second. Now Q is 0, that means saturated vapor, L equal to L bar. Remember L is same as L0, so in the top column reflux is saturated liquid, which is L0. So when it enters the column, we have the L equal to L0. That means we can write L bar as L0 equal to 1.3 moles per second, which is given to us. Now let's see, based on this, what else we can do. We have the overall balance F equal to D plus W. F is known, but D is not given, W is not given. F dot X, we can write the species balance D XT plus W XW. So again here XT and XW, the composition of the distillate and the bottom products are not given here. XF is of course given here. So it looks like from these two equations we are unable to determine the rest of the quantities. However, look at in the bottom column or the top column here, we have G which arrives to the condenser equals D plus L0. Alright, so the D on the vapor from the top plate when it arrives here is the G flow rate, and this is your top product D, and we have the reflux L0. So we can calculate the top product D as G minus L0. G 1.6 and L0 we have calculated is given 1.3, which is 0.3 moles per second. So we got D here. How about for the bottom column? We have L bar split into 2, W plus G bar. So W equal to L bar minus G bar. L bar we set same as L0, 1.3. G bar is the reflux, which is sent back from the reboiler as a reflux vapor, which is 0.6, 0.7 moles per second. So essentially now we got all the quantities. Now if you substitute in these equations, F is known, D we have calculated, W we have calculated, XF is known, but XT and XW they are not known to us. So this equation is still we are not in position to calculate. Okay, what else we can do? Now we can write down the operating line equations. So for the top column we have a general expressions yn plus 1 equal to r over r plus 1 xn, plus we have xt over r plus 1. So if we choose nth plate here, the vapor which arrives here has composition yn plus 1, and the liquid which leaves the nth plate has composition xn. So that's what operating line does. It connects yn plus 1 and xn by this equation, which was obtained, if you recall, by taking this envelope region and 1 around this condenser and this plate nth to have this material balance here. So we know the reflux ratio now, R equal to L0 by D. 1.3 is given to us. That reflux is 1.3 mole per mole of feed as sent as a condensate over D, which we have calculated as 0.3 to make it 4.34 here. So we know the slope of this operating line as R over R plus 1 as 0.81. So now we can substitute yn plus 1 equal to 0.81 xn plus xd, R plus 1 to make it 5.34. Alright, so now we have gotten equations which can give us the composition of one stream if we know the composition of the other streams here. So which is 1 and 2 here. We have this plate here 3, feed enters between 2 and 3. So this is y2 and this is x1. X1, since the total condenser is same as y1 and same as x0. Alright, so since the total condenser, we can write x0, which goes to this as a reflux, is same as y1 and same as your top product xt, but we do not know this xt. Okay, but we can write down the equations. Now we can connect y2 and x1, and we can connect y3 and x2. The two streams are in equilibrium, two streams are in equilibrium. Okay, so let's write down this equation for stage 1 or stage 2. Stage 1, if you recall, if you can write down these equations the way it is, all x0, y1, xt is the same. That will be the same as if we substitute here for x0 and y1. You will get the same result. Let's do it for stage 2. So when we do it for stage 2, y2 equal to 0.81 x1 plus xt over 5.34. So xt is not known to us. Okay, now x1 and y2. But remember, for the plate, this x1 is in equilibrium with y1, plate 1, and we have given the equilibrium line equations. So we can substitute x1 from y1 over 12.6. Remember, the equilibrium line equation is given as y equal to 12.6 x. Okay, so general expression we have. So since x1, y1, they're on the equilibrium line, we can substitute here. to obtain this equation xt by 5.34. But what is y1? Remember this y1 which arrives from the top plate to the condenser. We have this total condenser, y1 equal to same as xt. So we can substitute y1 here with xt to simplify these equations as y2 equal to 0.25 xt. So if we substitute, now we have another expressions which relates xt to y2. Now let's again try to see what we want to do here. Okay, first thing is that McCabe-Thiele method traditionally is you draw the two operating lines and find the number of trays. Now in this case, we know the slope r by r plus 1. We know all the vapor flow rates L and G, but we do not know the composition of the top product and the bottom product. So you won't be able to draw the operating lines and mark these stages here. So we are doing analytically, right? If you want to write down a program, there also you can write down this equation of the operating line. You can do the coding, and we can put a loop in all for all the stages for the top section and for the bottom sections. So here our strategy is that we have one equations analytically f d plus w. We know the flow rates, and when we write down the species balance f xf as dxt and y and bottom w xw, but we do not know xt and xw. So we just have one equations. We are looking for one more equations. So what we do, we start from xt. Xt is same as x1. X1 is in equilibrium with y1. Then you connect y1 and x2 till you arrive at the bottom. So now you establish one more equations between xt and xw. So now then you will have two unknowns and two equations. Then you can solve for xt and xw. Once you know the compositions, now you can mark all the composition on your graph or in your answer book. All right. So here we are trying to solve analytically. Why? Because we cannot solve graphically because the compositions are not known to us. All right. So let's continue with this. We have written, now we got the starting from xt, which is same as y1 because the total condenser. Now we have connected this to y2. Now let's do it for the third stage. Okay. So stage 1, stage 2. Now we have this stage 3. Mind you, this feed enters here. So this compositions and this composition. What is this composition? This is y3. And what is this composition is x2. Now still we can write down these expressions between x3 and x2. Alright. So this y3 and x2, the composition here do not change. So in this plate between 2 and 3, if you recall, we established Q line. What was the Q line? Q line, we had energy balance. Whatever energy is brought in here, we had energy balance between the two streams of vapor here and for the liquids here. All right. So now what we are trying to do here, that we are extending this operating line for the stage just underneath 2. So we started from xt, then we had this, got it in y2. Now we will write down the expression for y3 and x2. Okay, y2 and x2, they are in equilibrium. Y3 and x2, they will be given by the operating line. So we write down the same expressions now for y3. y3 equal to 0.81 x2 plus xt over 5.34. But again, x2, this stream is in equilibrium with this stream y2. So we can substitute from the equilibrium curve y2 over 12.6 plus xt over 5.34. So now we can write y3 0.81. y2 is given in terms of xt. So we can substitute here 0.25 xt over 12.6 plus xt over 5.34. So now we have another expressions, y3 as 0.20 xt. So this y3 is now known to us. Once we know y3, all right, we can calculate now x3. So this is third stage, and this is composition here is x3. So x3 will be equal to y3 divided by 12.6 equal to 0.016 xt. So let's try to understand what we're doing here. Again, let's discuss it. We have this feed which enters between stage 2 and stage 3. Now this is a mixing zone, okay, and we made use of energy balance. If you recall, we had the total balance F what enters and two streams L and L bar, and we have G and G bar. So we wrote down this. Go back to your lecture notes. We wrote down this overall material balance, and then we wrote down this energy balance or the enthalpy of all the 5 streams, 2 liquid and 2 vapor streams with the feed here. Okay, then we got this Q line. Now what we are trying to say here, that the compositions of the vapor arriving at the stage 2 underneath 2 is same as the composition of the vapor which leaves the number stage 3. So we wrote down this operating line for rectifying sections all the way till Y3 and X2. X2 is the composition of the vapor liquid which arrives from the stage 2. So we could write down the balance between Y3 and X2. Now we are in the stripping sections. So we have to now begin with the stripping line equations. So we are trying to substitute Xt in terms of Y1 total condenser, then Y1 X1, X1 to Y2, etc. till we have one more equation between Xt and Xw. Then we make an overall material balance or species balance. We'll have 2 unknowns and 2 equations. So let's continue with our balance with the stripping sections. Now the equation of stripping line, stripping section is Ym plus 1. So we are using now M instead of N. We have L bar by G bar, but G bar we write in terms of L bar minus W, Xm minus W over L bar minus W, Xw. So again we know all these quantities here. Only thing we do not know is this mole fraction Xw. So that's what we said in McCabe-Thiele methods. Even if you know the slopes, but if you do not know the compositions of the 2 products, you cannot draw this graphically. So neither Xt nor Xw's are known to us. So we are trying to solve analytically, and these equations can always be programmed for every stage. So you have to realize that all stages above the feed, okay, and all stages underneath this feed where it enters, we can write down 2 equations. One equation will hold good for all this, another equation will hold good for this. We can also write down this one equation for this Q line. So that's the way you have to do it if you want to do by programming. Here we are trying to write down this equation for every stage above this and every stage below this feed F. Okay, so we have the general expressions. Let's put the number. We know L bar by G bar, which is 1.3, and G bar we have calculated as 0.6 Xm. Actually 0.6 was given in the it's a preparation in the reboiler is 0.6 moles per feed. So we chose F as 1 mole per second. We have this G bar as 0.6 minus W. W is given as 0.7, so we can substitute here as 0.7. L bar minus W is same as 0.6. We have this Xw. So we can write Ym plus 1 as 2.16 Xm minus 1.16 Xw. Okay, so now let's see now how we can apply. So we have 3 plates, 1, 2, 3, and the 4th plate, theoretical plate, is from the reboiler. So we have this vapor composition which is Y4, and the liquid composition which arrives from here is X3. So Y4 and X3, they will be connected by this operating line. So now we can write Y4 equals 2.16 X3 minus 1.16 Xw. Okay, what is Y4? Y4 is in equilibrium with the compositions Xw. So when you have the reboiler, all right, the liquid arrives here. We are withdrawing the product W and Xw, and part of this liquid you are vaporizing it as G bar with the composition Y4, or remember Yn plus Np plus 1, where Np is the last stage. So we have 3 stages, so this is Y4 here, and the two streams are in equilibrium. So y4 we can write in terms of xw as 12.6 xw equal to 2.16 x3 minus 1.16 xw. But remember, this x3 also we calculated from the previous equations which we had, or operating line for this rectifying sections, where x3 was calculated as 0.016 xt. So go back to the previous slide here. X3 is calculated in terms of 0.016 xt. So we started from xt, slowly by writing these equations for every stages we have an expression xt in terms of x3. So in that we can make use here x3 equal to 0.016 xt, and we can substitute here to obtain another equation, 12.6 xw equal to 2.16 multiplied by 0.016 xt. So here we have substituted, alright, the values of x3 in terms of xt minus 1.16 xw. So now what we get one more relation between xw, the top product, and the bottom product. Xw equal to 0.03456 xt. So this is the second equation we have. The first equation we had f xf w xw plus d xt. F is 1. Xf was given mole fraction as 0.005 compositions. W we calculated as 0.3, or D we calculated as 0.3 into xt, plus W we have calculated 0.7 into xw. So we have, this was the first equations, and now we have the second equations 1 and 2. If we substitute, we should be able to get, if we substitute here to show that xt equal to 0.0165 and xw equal to 0.000041. So we have got two composition unknown quantities here, xt and xw. Now we can go back and mark this point on this McCabe-Thiele plot. We can draw the operating lines, the q lines, etc. Alright. So idea here is that once we get xt and xw, now we can do the back calculations to obtain x3, y3, x4, y4, or x2, y2, and x1, y1. Okay. So let's summarize this, the example which we have done here. The idea here is to solve analytically. Of course, graphically cannot be used because we do not know the compositions. So our strategy was to write down the operating line equations for both the top section and the bottom sections. Start from xt and see how we can substitute xt in terms of y1, then y1, x1, they are in equilibrium. Once you know x1, you get y2 again. So make use of this tie line and the equilibrium line, what we have been doing graphically on the McCabe-Thiele method. Same thing we are doing by the equations. So we are substituting one variable to another variable till we arrive at stepping sections, where we write another equation for the operating line, and slowly, so gradually we do the same exercise for the last stage, so that we have one more equations in terms of xt and xw. We have two unknowns, two equations we can solve. Now there are two ways of looking at this, as we said earlier. One is of course to solve analytically, algebraically. If you have set up all the algebraic equations, then there is no need for the graphing. The second is that you can also do this programming code. If you know Fortran or you can know C, you can have, you can write down this operating line equations for every stages. You can define variables like y for every stage, x for every stage. Molar flow rates are constant, so you can put some loop, do I equal to 1 to number of stages for the top column. Similar exercise you can do for the bottom column, bottom section of the column. Do I equal to 1 to how many stages, that many stages you have for this bottom column. And one can calculate, solve by writing all these equations. You can also call some numerical programming to solve set of algebraic equations. So that can also be done, right? So this is the way most of the engineering commercial software, they work when you have the equilibrium line equations, give equilibrium line given by some equations, and then you have two operating lines and you have the Q lines. All these four can be used in the programming code to solve set of unknown quantities. Okay, so that's our example. Now what we do now, as you said earlier, we discuss a very common distillation column, which is based on what we call open system. So if you have two components A and B, out of which one is water, so you have aqueous and you have another non-aqueous system. Okay, and if you want to distill, say the bottom product is your rich in water and top product is rich in some other organics. Okay, very ideal system, no acid drops. In that case, when you have the vapor reflux sent back to the distillation column, it will be rich in water, right? So if you have that type of situations where your bottom reflux, the vapor reflux, is highly rich in water, say 0.999%, less volatile component here, then there's no need to put physically vapor, this reboiler here. You can have a steam available from a nearby plant neighborhood that can be sent as a reflux. Okay, so let's continue with this new topic here, use of open steam. Okay, so what we have here is a distillation column. Okay, we have stages here. Feed is sent somewhere here, F with composition with the flow rate F and XF. We have the top product withdrawn. Then we have this condenser. So this is a product here, D and XT. Let's say it's a total reflux, and the reflux is saturated liquid. So we have this reflux ratio R equal to L by LD. This goes to this top plate here. So we have this X0. This is Y1, which is same as this Y1. So Y1 equal to XT equal to X0. Now the system which we have here is, let's say, A plus B. B is, let's say, less volatile, is water, and A is more volatile, some different component here, which is going to be distilled as a top product. Okay, so you will expect that this XT, let's say, is a very highly rich in A, let's say it's 99% here. Okay, now the bottom product, the liquid which arrives from the bottom plate to this reboiler, typically this will be rich in the other components B and very poor in this bottom product. So what you will do here, this liquid will be reboiled, part of this vapor, part of this liquid will be sent as a vapor reflux as G bar, and here you have this bottom product W and XW. So this XW will be, let's say, 0.001 mole fractions. Okay, so it's very poor in this A but rich in water. So this reflux vapor, which is sent back to this distillation column from this reboiler, is nearly water. Okay, so if you have this type of situations where one of the two components, the less volatile, is water, okay, and your bottom product is highly rich in water here and very poor in the top product, you will expect that the reflux will also be very rich in water. In that case, one can do away with this arrangement of reboiler, and essentially what you will have a bottom, this is the bottom tray here. What reflux you will send back will nothing but pure steam. You can say that composition of Y is, say, this number of plate is NP, this Y NP plus 1 is 0, approximately 0. So whatever product you are getting L bar is nothing but your bottom product. So this is what we are calling it as an open system. We have the bottom product, bottom column, in which whatever liquid we are withdrawing is highly rich in water. So the reflux which is supposed to be sent from the reboiler is nothing but steam, pure water. We can this steam may be available from some nearby plant. So from there we can take a steam and send back to the distillation column where there is no reboiler. We call this as an open system. Now how do we address this type of situations? Based on whatever we have learned in this course in this McCabe-Thiele method. So McCabe-Thiele method, essentially what we do, we write down the species balance or the material balance for the top column and for the bottom column. So you have two lines, two operating lines, they intersect, you have this Q line, then you calculate the number of plates. You can also have a Ponchon-Savarit methods where you recall you have HV, saturated vapor composition enthalpy, and saturated liquid enthalpy. There you locate the difference points at the top XT and the bottom as XW, and then you mark your tie lines and the operating lines. Okay. In this system what happens when there is no reboiler? So we'll have to make certain modifications in both McCabe-Thiele method as well as in Ponchon-Savarit methods. The idea is that how we can address starting from the first principle or by making some analogy on both the methods, Ponchon-Savarit methods and McCabe-Thiele methods. Okay, so let's see what we do here. So let's write down the operating line equation. Which is yn plus 1 equal to r over r plus 1 xn plus xt over r plus 1. So r by r plus 1 is nothing but L by G. Okay, so that's one equation. Second operating line equation we had for the stripping sections, which we wrote as ym plus 1 equal to L bar over G bar xm minus W. So here we have actually W xW over L bar minus W. Okay. Overall we wrote as F equals D plus W, and we wrote F ZF equal to D xt plus W xW. So we have this McCabe-Thiele method. Where this is xt, this is xw. So we draw this operating line, we have another operating line here, and wherever it intersects at xf we have this q line. Okay, so now in our case when there is no reboiler and we have direct steam and we have the bottom product L bar, which is nothing but our product here W. Okay, this is G bar here, which is nothing but the steam flow rate. How we can modify this approach and do the same calculation what we were doing earlier. So you must realize that the operating line equation for the top section will not change, which means if we take this envelope underneath this plate number n, we have yn plus 1 and we have this xn. So this equation is unchanged. R over r plus 1 xn plus xd over r plus 1. So this is unchanged. Now for the bottom column, now we have this mth plate, right? So what we have done here is, so this mth plate, and we took this envelope like this. So this is stream which arrives here is ym plus 1. The stream which is arriving here is xm. This flow rate here is L bar, this flow rate here is G bar, and this liquid L bar, we know that this bottom product W, and the vapor, which is nothing but pure steam, is G bar. So we have this Y, which we said an NP plus 1 equal to 0. So there is no reboiler here. So what happens to our balance here? Overall balance F plus G bar. So this is F plus G bar equal to D plus W bar. Mind you, this W bar is nothing but L bar. So compare this to the earlier case where we had F equal to D plus W. Now we have F plus G bar, that's what enters, equal to the top product D which leaves, and L bar or W. So this is the new equations we have. Let's make now species balance here. So when we say operating line, either for the top column or for the bottom column, is nothing but the species balance for that region. So when you make the region balance here, now L bar XM is what you have here, two streams, the stream which enters this region or envelope which you have drawn here, plus G bar into Y NP plus 1, but that's 0. So these are the two streams, equal to what we have here is G bar Ym plus 1 plus W or L, which is nothing but your L bar into XW. See, compare this to the previous case where there was one product which was W here. Then when we wrote the balance here, then we had L bar XM, this term here, we had this term here, plus we had the last one. Okay, but now what we have here, this compositions is still 0 here. So if you simplify this, you will have the equations of operating line as Ym plus 1 equal to L bar over G bar XM minus W over G bar into XW. So now let's compare with what we had earlier and what we have now. Previous operating line equations which we wrote, we had L bar by G bar and we had W by G bar, but L bar was not same as W. Alright, so we had the flow rate L bar arriving to this reboiler, we had this bottom product which was W and sent back as G bar. Here we are saying that there is no reboiler, so this product L bar is nothing but the product here W. So these are new equations where L bar equal to W. Okay, so we see one modification here in the overall balance, and we see this balance difference equations which is format is the same except that L bar is same as W bar. So let's see how we can model or how we can plot on this McCabe-Thiele method. So we realize that equilibrium curve is the same and the operating line equation for rectifying section is the same. So what the equation which we have for the top, Yn plus 1 equal to R over R plus N Xn plus Xd over R plus 1. This point Xt also satisfies 45-degree line, which means at this point you can take a slope or intercept of this Xt by R plus 1. We had this operating line. So this Xt equal to Yd, if we substitute here, you will get this 45-degree line. Okay, in the earlier case, similarly we took this Xw here and we took the slope to connect here this point here, which if you extend and connect this to Xf will give you Q line. But notice here that now what we have at the bottom is this L bar, which is same as W, has the composition XW, but the vapor which arrives has a composition 0. So in the previous case, again when you wrote down the expressions for your operating line as Ym plus 1 equal to L bar over G bar Xm minus you had W over G bar as XW, we said that when you substitute XW here, then this line will again satisfy will also line on this 45-degree line. So ym plus 1 will also be equal to same as xw. That's why we extend this to this point. But now L bar is same as w. Alright, L bar is same as w. That means when you put xw, you will get y0 equal to 0. That's what we have here. So this is ynp plus 1 actually, which is 0 here. So what happens to that? Now the points here, now they don't lie on this 45-degree line. Now what you will have, xt, connect with the slope or the intercept, whatever you have. But now y equal to 0 corresponds to your xw. In other words, this is your y np plus 1, which is 0, pure steam, and the liquid which trickles down as a product is xw, as a composition xw. This flow rate L bar is same as w here. So now we have this point xw right here, but no more we have this y equal to xw, because now we have different equations in which you substitute xw, you will get y equal to 0. So this is the point you have. With this point, if you take the slope of L bar by G bar, that's ym plus 1, let's rewrite here L bar, which is same as w over G bar into xm, minus you have w over G bar, and here you have xw. In this, if you put xm equal to xw, you will see that since L bar equal to w, you have 0 here. So now with this and with this slope, or with the intercept, negative intercept, now you have to connect like this. This will now correspond to your xf or the q line. So notice the difference here. Instead of connecting from here, right, now you have connected with this x-axis where y equal to 0, because this is what operating line connects. The two phases, phase which arrives here, the liquid which leaves here, operating line connects like this. So for the bottom tray, we have y np equal to 0 because it's pure steam, and xw is a bottom product composition which is known to us. We mark the point here, and now we connect to obtain this intersection. So these would be the two new operating lines. Remember again, instead of starting from here, we have to start it from here, because earlier xw also xw equal to yw also satisfied this operating line equations. Now y equal to 0 and xw, they satisfy this equation. So we have modified this McCabe-Thiele method. Alright. Now again, you should go back and carefully see that this open system or open steam system, whatever we're calling it here, is nothing new. New in the sense that our approach remains the same. You write down this operating balance equations or species balance equation for this bottom envelope, the sections underneath the feed, to realize that there is a modification in the overall material balance, and there is a modification in the species balance for this stripping sections here. And then modification comes from realization that we don't have a reboiler. L bar is nothing but the bottom product W, and XW, which is the compositions of the stream which is leaving the distillation column, has corresponding vapor phase compositions which is 0 because it's a pure stream. So that coordinate does not lie on the 45-degree line. That coordinate lies on the x-axis. From there you have to connect to the operating line. Otherwise all the treatments are the same. You can start from the top or from the bottom and can construct the trees here. Now the same argument should also hold good for Ponchon-Savarit methods. Remember, in the Ponchon-Savarit method also we located the two difference points. That's the key. One is xt or del xt, and one was del xw. Okay, so we had q dash, a living stream has q dash energy, and the living stream at the bottom has q dash. So all we do that the top xt will remain the same, q dash will remain the same. However, this xw or q double dash, which we had in Ponchon-Savarit methods, will be now different. So let's locate in what way, where does that coordinate lies, and how we can calculate this point. Okay, so when we do this Ponchon-Savarit method, so what we had earlier when we had the reboiler, we had the two saturated vapor and saturated liquid enthalpy curve. Then we said that corresponding to this xt, say in case of total reflux, we mark this point del xt, which corresponds to the coordinate q dash, which is qc condenser load plus dht. So a hypothetical stream leaving the system with the condenser load and the top product divided by d. So that was our q dash, which is nothing but net, we said net heat or energy out over net molar flow rates, net molar flow rates. So what is this net molar flow rate? Nothing but d, the d equal gn plus 1 minus ln. So at any plate, the vapor flow rate gn plus 1 and the liquid leaving ln, the difference is same as your top product. So this is net molar flow rate, net heat out. Of course the stream leaving is d, but we also included the condenser load here, q dash. So we mark this point. Similarly, same thing we did it for the bottom product, where we had this xw, and we said that q dash corresponding to this del xw point equals w hw. So that's the enthalpy leaving the system, plus here minus you have this qb, you are giving the energy here, divided by this w. So same definitions, net heat out divided by the net molar flow rate sub w. So for any bottom trace we have gm plus 1 and the liquid leaving is lm, so the difference is same as w here. So the definition for q dash and q dash is the same, net heat out or net molar flow rates. Okay. Now what happens in our case when we have this open system? So we have this bottom plate, alright. From the bottom trace we have w, which is nothing but L bar composition xw, and we have this vapor which is gnp plus 1 with the composition y np plus 1 equal to 0. It's a pure steam. So the top locations in the Ponchon-Savarit method, if you redraw here, will not change. What will change here is xw. So we have to locate where is this new locations of this xw. So what are the definitions for x del w? Again, whatever is leaving from the bottom product, which is nothing but wxw, over the net molar flow rates, which is w minus gnp plus 1. So this equations, when you put this as 0, gives you same as what we had before here. Now the compositions of this hypothetical stream which is leaving the system is wxw by w minus gnp plus 1. So this stream will also have a modified heat energy leaving, which would be w hw. So this is the energy leaving, heat leaving the bottom plate, minus what we add here is gnp plus 1 h gnp plus 1. So this would be the enthalpy of the steam, saturated steam, which goes under to the column. Net molar flow rate is not w minus gnp plus 1. So look at the difference. We said that bottom w earlier was g m plus 1 minus, or it was actually w was difference of L np minus g np plus 1. But now we have the net molar flow rate as w minus gnp plus 1, because we have this pure steam here. So all we'll do, this composition x del w and q dash has not changed here. So what xw here is here will now be different. We have to mark this new del xw and new q dash here. So we get a new coordinate here, new difference points, and then we can do the constructions what we had earlier. Remember, this gnp plus 1 has y equal to 0, so we locate this gnp plus 1 here. If you connect with this xw, now you will get a new coordinate, from where now we can say that this is in equilibrium with gnp and then we can keep on constructing this, and we can draw this drawing. So let's just redraw this Ponchon-Savarit method graph again. We have HV and we have HL, and we got this new data point which is Q dash, and we have this X dash, new mole fractions here, right? Now we have the calculation for XW as WXW W minus GNP plus 1 net molar flow rates, and Q dash is also net total enthalpy leaving minus GNP plus 1 HGNP minus 1 over W minus GNP plus 1. So with this, now we can connect. This is your YNP plus equal to 0. So we have GNP plus 1 on this axis. We connect with this new del point. Once we have this, then we can construct our new tie line, which will correspond to GNP. Again, we connect here with this, which is LNP minus 1, and so forth. We can construct here. All right. So this is a discussion we had for this open system. Now again, try to look at this problem slightly different way. Like what we're trying to say here, that we can still apply the same approach what we learned for McCabe-Thiele methods and Ponchon-Savarit methods based on material balance or the energy balance. So here now we have to look for the new difference data points. If you apply for Ponchon-Savarit methods, Ponchon-Savarit method, the top product has not changed, quality has not changed, except at the bottom we have a new difference points. Why? Because now we don't have a reboiler. Now we have one stream which enters the top, enters your region or the envelope which you have drawn, and the bottom product leaves as a L bar, which is same as W. So you have to slightly modify. You have to make use of same definitions for your del D, XW, Q dash or Q double dash, except you have to ensure that you are inserting the new numbers for your net flow rates. All right. In McCabe-Thiele methods, we also have the same approach. Now we wrote down the operating line balance till we realize that the compositions y equal to 0 corresponds to your XW. Earlier, when we didn't have open system, we had a closed system. We had only one product which was leaving the envelope of our calculations, and there we had XW equal to YW falling on this 45-degree line from which we connected. So again, I should go through the textbook and see if we can solve a very simple example here. All right. So that concludes today's lecture.